Okay. What is that? Once we need to go Alt, Control, Alt Shift. Move from once, otherwise I have to keep moving. It is Control Alt. I don't remember what it is.
Ma'am, first share the whole desktop, then alter tab.
Alt tab, right? Okay.
Yeah, you'll have to share the whole desktop.
1 second. No. You can see the PowerPoint presentation, right? You can see the PowerPoint presentation.
Yes, ma'am.
Okay. Can you check in your textbook? It is page number that you have the all the different objects with their moment of inertia. Can you see solid cylinder? Because you should know you need to by heart all those formulas. Can you check solid cylinder? Anyway, I have given the value. A solid, yes, yeah, yes, boys. A solid cylinder rotating about its own axis. The moment of inertia is I is equal to half mr square. So what you do is, boys, whenever you are solving a numerical, keep on paper or any notebook so that the formulas immediately you note down. Like, uh, these are the things which you have to by heart. I is equal to half mr squared. Now the question is, what is the kinetic energy associated with the rotation of the cylinder? So it's rotational kinetic energy. You know rotational kinetic energy is half I omega squared. It's direct substitution. Will you be able to do this, boys? Just calculate the value of your kinetic energy. So I is half mr squared. Calculate. You can directly substitute.
Ma'am, where do we write this?
You write it in your notebook, no problem. Just
Okay.
write. It is no need to copy down the question. Just write 7.1 to text.
Okay, ma'am.
I is equal to 0.625 kilogram meter squared. Your formula for kinetic energy is half I omega squared. For momentum, angular momentum, L is equal to I omega. For angular momentum, L is equal to I omega. Actually, L has angular momentum has different value. It is P into R, linear momentum into R. Here, since we are dealing with moment of inertia, I am using L is equal to I omega. I think so. You people can calculate. So kinetic energy, the SI unit will be in joules. Okay, what is the kinetic energy, boys? Answer. What will be your answer for kinetic energy? Is it 0.625? The rotational, can you see the slide? Can you see the slide of the PowerPoint
Yes, ma'am.
presentation?
Yes.
Yes,
Ma'am,
ma'am.
there was a little lag, yeah, but yeah. Ma'am,
Yes.
could you explain what you did in the previous box, like the
Which
bottom
one?
left? Bottom left box.
That is, I have found moment of inertia. I is equal to half mr squared. If you check, okay, you can check your textbook, because textbook you have for cylinder, for ring, all those things with the axis of rotation, what will be the moment of inertia? So you have to refer that. So for cylinder, generally, if at all cylinder is being given, you have to by heart this formula. I is equal to half mr squared. Then same way you can calculate your angular momentum. It is I omega. So what is the value of angular momentum? Is this what you are getting? Sorry, boys, this is 1 second. 0.625. The value is angular momentum. Because here the value is, it's I omega. Okay, so angular momentum L is equal to I omega. So I is 0.625, omega is 100. So it becomes 62.5. The SI unit is, look at the angular momentum. It is linear momentum into distance. Linear momentum is kilogram meter per second into meter. R is in. So it becomes kilogram meter squared per second. This is the SI unit for your angular momentum. Kilogram meter squared per second. Torque is newtons into meter. Kilogram meter squared per second. Have you completed this, boys? 11B?
Yes, ma'am.
Yes, ma'am.
Okay, I'll go for the other one.
Okay,
Yes,
ma'am.
The next one. Okay. A rope of negligible mass is wound around a hollow cylinder. Just check, boys, what will be the moment of inertia for the hollow cylinder? What will be the moment of inertia of a hollow cylinder? Okay. Can you imagine this is a hollow cylinder? I'm looking at the cross section of the hollow cylinder. I'm looking at the cross section of the hollow cylinder. So you have a cylinder, which means this will go like this. That is what it means. So a hollow cylinder of mass 3 kilogram, radius 40 centimeter. So a rope is wound over the hollow cylinder. Then what is the angular acceleration of the cylinder if the rope is pulled with a force of 30 newtons? And what is its linear acceleration? So the question is, what is angular acceleration as well as what is linear acceleration? If you can see for hollow cylinder, see now when you pull this rope, when you're pulling this rope, now this cylinder is going to rotate about an axis passing through its center, and along the axis, this cylinder is going to rotate about an axis. Yes, sir? Can you imagine? This is only the cross section of the cylinder, boys. It will be like this. Only the cross section of the cylinder you are looking at. Right? It's going to move like this. It's going to rotate like this. which means it is rotating about an axis. Here you have to imagine it's rotating about an axis, which is passing through its center. So then the moment of inertia is I is equal to mr square. See, you can rotate a cylinder this way also, right, boss? I can rotate a cylinder about this axis. I can rotate the same cylinder about a line this way also. I can rotate this way or I can rotate this way. So when you're putting a weight over here, the cylinder will rotate about its own axis. So moment of inertia of hollow cylinder about its axis. Okay. Now the question is, what is its angular acceleration? It's tough, boys. 8 o'clock is tough for you all. In case if next Saturday, if I need to have a class, which would be better time? Moment, around 9 o'clock.
Around 10, yeah.
Okay. Next week, in case if I need to have additional class for gravitation, then in that case I'll go for. I thought this would be better for you. Fine, boss. So moment of inertia of the hollow cylinder about its axis. So I want to know what is the angular. Always you need to write what is given. What is given? Mass is given. Radius is given. Force is given. Whenever you solve a numerical, write what are the physical quantities given and write what are the physical quantities to be found. So angular acceleration alpha to be found, linear acceleration a to be found. Is that clear, boys? So now, how will I find angular acceleration? Now look at this. You know, torque is equal to force into. This is torque, boys. Whenever the torque is a force which is going to produce rotational motion. Torque is force into, see, but this is your axis of rotation. Axis of rotation. So what is torque? Torque is a force which makes the body to rotate. So torque will be, so this distance is r. So from the force, right? This is the point of application of the force. From the force, how far is your axis of rotation? So torque, tau is always equal to force into the distance. Here the distance becomes equal to the radius. Can you imagine, boys? The distance becomes equal to the radius. This is your force. Okay.
Yes,
The
ma'am.
distance, the axis of rotation is passing to the center. So next class, in case if it is Saturday, you tell me, boys, which time is favorable for you, right? So torque is equal to force into distance. Then I have to, then what about torque is also equal to I alpha? Are you clear, boys? See, I think so. I need to go for some formulas here for 1 second. So there are different formulas for torque, two different formulas for torque, two different formulas for, if you can just write somewhere, angular, yes boys, angular momentum, boys, angular momentum. So torque tau is equal to F into R. Angular momentum L will be equal to P into R. P is, so tau in terms of moment of inertia, it is I alpha. In terms of moment of inertia, it is I omega. So these formulas for torque and angular momentum you have to, because throughout the chapter, these are the formulas which you are going to use. So mark this as equation 1, mark this as equation 2. You all had your breakfast? No.
Yes,
No.
You have your breakfast, keep having and write. Next class, in case next Saturday, you just inform me, boys, which would be better time for you. Okay, torque and yes,
Ma'am, hello.
yes.
Ma'am, could you go back to the previous slide for a minute?
Which slide? 7.1.
Yeah.
7.12. Now I'll let me, because if I'll erase this, I cannot come back to this. 1 second. I'll finish this and I'll go.
Okay,
Next.
ma'am.
Now, can you equate these both, boys? Can you equate equations 1 and 2? Equate
Yes, ma'am. Just a second.
1
What do
and
you mean? Assume there is no slipping in the question. It's clear.
yeah, that's it. That's the thing we'll consider. Assume there is no slipping.
What is slipping? Like, what do you mean
Slipping in that sense, suppose when a body is sliding down an inclined plane, right? When his body is rolling down an inclined plane, it should not skid. So when you're pulling it, the cylinder should not move out. That's it. That is our no slipping in that. That is the condition over here. When you're pulling the rope, the cylinder should not move away. It should only rotate. It can only rotate. It should not. Yes.
Ma'am, my angular acceleration is equal
Yeah,
to 1
okay.
plus 4.
Equate 1 and 2 and get me an expression for alpha. What will be
Yes,
alpha?
ma'am. Alpha is equal to 1 by 4.
Correct. Fine. So you have got the value of alpha. What will be the SI unit? What is SI unit of angular velocity? 1 second, boys. SI unit also.
Radians per second square.
Correct. Radians per second square. 1 second. If you all have doubts, boys, in that case, theta is angular displacement. Was theta is angular displacement, that is in radians. Omega is angular velocity, that is radians per second. Angular acceleration, sorry, is omega by t, so that will be radians per second squared. Is it because 40 centimeter you have to convert it to meters per? Can you see this? That is why it is 25 radians per second square. So what is this? This is angular acceleration, boys. Angular acceleration. Radians per second squared. Boys, if you would not have, sorry, if you have not taken your breakfast, bring your breakfast. You have your breakfast as you are learning. So
Okay.
alpha is equal to 25 radians per second squared. Next time you decide which time is feasible for you all.
Okay.
Now, what is the relation between linear acceleration and angular acceleration? So linear acceleration. So that's the reason I'm telling you, keep a separate paper or a book so that whenever you're writing, coming up with a formula, you keep writing the formulas, or else you can't do the numericals, boys. You keep writing the formula. You, sorry, you keep writing the SI. Did you understand why this is 10 to the power of? Because your radius is in centimeter. I have to convert it to meter. 40 into 10 to the power of minus 2 meters. So linear acceleration, A is equal to R alpha. This is one more formula, boys. So you had a formula, tau is equal to I alpha. Torque is equal to I alpha. Torque is also equal to F into R. Then you know how to write the SI unit of angular acceleration. And one more formula, linear acceleration, A is equal to R alpha. Will you be able to hear also that radius should be converted to meters?
Ma'am, here they asked for the linear acceleration of the rope. So will
Yeah,
that
correct.
be the same?
Same. Because
Okay.
whatever the cylinder is undergoing angular acceleration, see the force, this is the direction of your linear acceleration, right? It will be the same.
All right, ma'am.
So as the cylinder is rotating, it has both angular and linear acceleration. So what is the value of A?
Ma'am, is it 10 radians per second?
Is
Right?
it 10 meter per second?
Correct. 10 meter per second square. Once.
Ma'am,
Yes.
we can find that using F equal to ma also, right?
Yeah, you can find F is equal to m into A, but how will you get A? Mass is given, right? Correct. So what is the force? 30 by 3. But will 30 by 3 gives you, can you just check? See, 30 upon 3. Oh yeah, correct. You can find that way also. Yes, boss. Fine. Once you have completed, let me know, boss. I'll move on to the next one.
Ma'am, this is only valid if there is no slipping, right? So
Yeah,
you can
correct.
think it's equal.
Yeah, it will be equal. It will be whatever the cylinder, as it is rotating, it will have both angular acceleration and linear acceleration. So the linear acceleration of the rope as well as cylinder will be the same. Don't skip your breakfast. You bring your breakfast. Keep having your breakfast, boys. Don't skip.
Ma'am, can you go to the previous slide now? Thank you.
I think you have completed this. I can go for the next.
Yes, ma'am.
Now look at this. I think I'll give you time for you to do. Torques of equal magnitude are applied to a hollow cylinder. What is this? Hollow cylinder. The cylinder is rotating about axis of symmetry. You know that what is the axis of this one? This way of rotating. So it's a hollow cylinder. So you must check your textbook. What is the moment of inertia for a hollow cylinder and a solid sphere? Can be this way also. Here, this is the axis of symmetry. This is for a hollow. For hollow cylinder as well as solid sphere. So now which of the two will acquire a greater angular speed after a given time? So first, write what is something that is given in a numerical. Always when you solve a numerical, you need to write what is being given. Then you have to write what is to be found. So the question is, what is the angular speed? Now think over what is given. Torques of equal magnitude, which means the torque which you are applying on the cylinder should be equal to, so tau 1 must be equal to tau 2. Okay, what is the general, there are two formulas for torque. What are the formulas, boys? Torque is equal to force into perpendicular distance. Okay, tau is also equal to I alpha.
I alpha.
So first find alpha, then we'll go for omega. So for the first one, for the hollow cylinder, tau 1 will be equal to I1 alpha 1. So tau 2 will be equal to I2 alpha 2. This is for the cylinder, this is for the sphere. So now equate both, because what is given? Both are undergoing the same torque. So tau 1 must be equal to tau 2. So get what is alpha 1 and alpha 2. So acceleration, when the speed increases, acceleration will also increase. Based on that, you can write. Boss, is this clear what I am doing?
Yes, ma'am.
So tau 1, if I'm writing tau 1 will be I1 alpha 1, tau 2 will be equal to I2 alpha 2. So what is being given? Tau 1 and tau 2 are the same. So equate them. And then get an expression for, that is what we have done. Get an expression for alpha 1 by alpha 2. So is it alpha 1 by alpha 2 is 2 upon 5?
Yes, ma'am. MR square will get cancelled.
Okay, so alpha 2 is greater than alpha 1. So angular acceleration of the second body, solid sphere, is greater than the angular acceleration of hollow cylinder. So therefore, acceleration is greater means naturally the speed will also be greater. So solid sphere has greater angular speed. First, those who haven't taken your breakfast, have it for a long time without breakfast, don't sit. Have something.
Ma'am, when is the class ending?
Now let me see how much time it will
Just
take.
to know, like, how much time should I?
No, it will take, was I have given
Okay,
have
ma'am.
it as 9 o'clock. So that's what I'm telling. You keep having your breakfast. So next time when I'm putting a message, just suggest boys, because if you want a different timings, I'll change. Because I thought if I can finish by 9, then you can do your other work. That's the reason early morning, if I thought I'll finish the work. Please do write, because I thought you people accepted it, so I continued with this. So take your breakfast or eat something. Don't sit without having food. Take something, you have your breakfast and start doing your work. So solid sphere has greater angular speed. Have you all completed 11B?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Shall I go for the other one? Next one. Because what I'm doing is all textbook numericals. That's where. This I'll come back. This is direct substitution. Okay. This you should understand the concept, boys. Before I'll do this, I think so. Some video clippings, we have been watching a video clipping. Did you remember? So a person having weights on his hands, sitting on a turntable and rotating. When he stretches his arm outward, his rotational speed decreases. When he brings his arms closer, have you seen the rotational speed increasing?
Yes, ma'am.
Do you understand that concept? When you stretch your arms and sit on a rotating table, what is going to happen? Your speed of rotation will be less. When you're bringing it closer, your speed of rotation will be more. Did you?
Ma'am, should we
Yes?
write these questions?
No. Only the question number is enough. Okay. Now, was 1 second, because before going for this, a concept is that we have seen what is the relation between torque and angular momentum. Relation between torque and angular momentum. relation between torque and angular momentum is tau is equal to dl by dt, right? If no external force is acting on the system is rotating. If no external torque is acting on the system, then dl by dt is a 0, or I can write L is a constant. So what is L? Angular momentum. In terms of moment of inertia, I omega will be a constant. Or I can say I is inversely proportional to omega. But still this you write, then again I need to explain. Just write, boys. This is what we call it as conservation of angular momentum. The law of conservation of angular momentum. Law of conservation of angular momentum. When there is no external torque acting on the system. Law of conservation of angular momentum, relation between torque and angular momentum. So I can write when external torque is 0, tau is equal to 0, then dl by dt will also be equal to 0. Or I can write L will be a constant. Only when you differentiate a constant, you will get 0. But whenever you differentiate a constant, you will get 0, because when will you differentiate? See, dl by dt is 0, which means your L is a constant. Your angular momentum is not changing with time. That is what it means. Your angular momentum is a constant. So any constant value, if you differentiate, it becomes equal to 0. Suppose y is equal to 2. What is dy by dt? It is 0. Because 2 is a constant. 2 is not going to change with time. Are you clear, boys? If I say y is equal to 0, then dy by dt is 0. When y changes with time, because y is having a constant value, constant will not change with time. So dy by dt is 0. Same way, when dl by dt is equal to 0, L is a constant. Now what is L? I omega. So I omega is a constant. First write this, boys, because I need to explain this.
Ma'am, this is a part of the question.
Yeah, this is a part of the question. This is a part of the concept, and then I have to come back to the question. Very, very, very important reasoning based, new application based, all questions based on reasoning. Applications are from law of conservation of angular momentum, not only momentum, but angular momentum. Should I write it properly? Should I go?
Ma'am, could you just explain it like again once quickly?
Oh, 1 second. Should I go for the video clipping, or this is fine for you all?
No, this is fine, ma'am.
Okay, boys. So, see, law of conservation. I have to go for the other PowerPoint presentation. Law of conservation of angular momentum. Now, what does it means? Means, suppose, boys, suppose a body is rotating. When a body is rotating, a certain angular speed, right? So it keeps on rotating with the same speed unless and until you apply a torque. Only when you apply a torque, the body gets accelerated. It undergoes angular acceleration. If there is no torque, the body will continue to rotate with the same angular speed. That is what is your law of conservation of angular momentum. Now, what is the relation between torque and angular momentum? Tau is equal to dl by dt. When there is no external torque acting on the system, when tau is equal to 0, dl by dt is equal to 0, or I can write L is a constant. So what is L? L is angular momentum. So L is a constant. What is the value of L in terms of moment of inertia? It is a constant. Now look at this. I is inversely proportional to omega. Omega means angular speed, right? Copy till this, boys. Then I'll have to explain how angular speed increases when moment of inertia decreases. I have to explain. I have to erase this. So I is inversely proportional to 1 by omega. If you have completed, then I'll proceed with this. Anyway, I'll stop till at 9. I'll sharp at 9. I'll stop. So I is inversely proportional to omega. Now let us see what does it mean. If you have completed, just tell me that you have completed writing.
Yes, ma'am, completed.
Oh, now we'll see that.
I'm complete.
Okay, 1 second. I is inversely proportional to omega. Now what is I? It's moment of inertia, mr squared. So what is that? What is moment of inertia? How difficult it is to rotate a body, right? A body cannot be rotated. See, if a body is already rotating, if you're when the blades of the fan is rotating, the moment you switch off your power supply, the blades will not come to a stop immediately. It takes some time. So that inability of the blades to come to a stop immediately, we call it as moment of inertia. Now, suppose if I have a rigid body, it has so many particles, say M1, M2, Mn, then angular velocity omega. So now what is, suppose if I consider all the entire center of mass is located, here, the center of mass is located at this point. So this is at a distance of r from the axis of rotation. Instead of considering all the particles, let me consider the entire mass is concentrated at this point, M, right? At point. Entire mass is center of mass. Entire mass is concentrated. This mass is at a distance of r from the axis of rotation. Is that clear, boys? So if the mass is far away from the axis of rotation, if the mass is far away from the axis of rotation, that is r. If r is going to increase, is that not your moment of inertia increases? Is that not the moment of inertia increases, boys?
Yes, ma'am.
Okay, now look at the other statement. So I is inversely. Suppose you're sitting on a turntable and you are rotating, boys, right? You're sitting on a turntable and you're rotating. You're stretching your hands. You're stretching your hands and rotating. Now what happens? Your mass is being, this distance increases. So this will be axis of rotation. How do you rotate? You're sitting on a turntable and rotating. So this becomes your axis of rotation. This is your axis of rotation. Can you imagine? You're rotating
Yes.
about an axis which is passing through you. You're stretching your hands. When you're stretching your hands, are you not? Your mass is being, because your mass is distributed through your hands also. So when you're stretching your hands and sitting on a turntable, your mass is being distributed away from the axis of rotation. Right? Your body mass is distributed away from axis of rotation, which means R is going to increase. You're stretching your hands, the distribution of the mass of your body is going to increase. R increases. What is moment of inertia? mr squared. When R increases, I also increases. When I increases, what happens to omega here? When I increases, omega should decrease. That is why when you stretch your hands, right, you are sitting on a turntable and rotating. When you are stretching your hands, your speed of rotation will be less. Okay, when you are bringing your hands closer to your body, suppose you bring your hands closer to your body, in that sense, you bring your hands closer to your body, then this R means how far is your mass distributed from the axis of rotation. Is that not in the second case, R is decreasing?
Ma'am, but one question, ma'am, how can a body rotate without torque? This condition is applicable only when torque is 0, but like for
No, the body is already in, no. See, once the body is under rotation, The body is rotating, but you're not applying an additional extra torque. See,
Yes, ma'am,
what
but to
happens?
start rotating, we need torque, right?
No. You consider Newton's second law of motion. 1 second. You consider Newton's second law of motion. What does it tells you? When there is no external torque acting on the body which is in motion will continue to be in motion, right? The body is already in motion. Newton's second law of motion. Think of Newton's second law of motion. When the body is in motion, look at this. Suppose if a body is moving, right? If a body is moving with, say, with speed of 50 meters per second. Now you are applying a force of 50 newtons on one end, force of 50 newtons on the other end. What will be the total force? What will be the total force? Zero. It's a balanced. The force is a balanced force. Do you understand Newton's first law of motion? What does Newton's first law of motion tells you? Whenever an unbalanced force, unless and until an unbalanced force acts on the body, unless and until an unbalanced force acts on a body, the body will continue to move with the same speed. Same way here, in that case, if your external torque is unbalanced, see, what you mean is that without torque, the body cannot rotate. But the torque, see, when you talk about your, 1 second, suppose if you want to rotate a body, 1 second, suppose if I want to rotate a body about this point, then I should apply a force. We call this as coupling. It has to go like this.
Yes, ma'am, you have to apply force.
But yeah, force. But these forces are equal in magnitude, opposite in direction. Only then you can rotate your body. It doesn't mean there is no torque acting on the body. If the torque is not acting, the body cannot rotate. But whatever torque is acting is a balanced torque. Balanced torque in that sense, both, see, torque can be brought about only by a force. One important component of your torque is a force. So these forces should balance each other. If this is 5 Newton, it should also be equal to 5 Newtons. So what the conservation of angular momentum states is that actually it should be external unbalanced torque. When you understand, when your torque acting on the body is a balanced one, which means the forces are balanced force. Only in that case. So you have to relate it to your Newton's second law of motion. Without torque, the body cannot rotate. Already there is a torque, but that torque is a balanced one. Because the force which brings about the torque is nothing but a combination of two forces. We call it as a couple, the moment of the couple. So when we study about the equilibrium of rigid bodies, we'll understand that better, because I thought I'll take it to the last topic of your chapter. There you'll understand, right, boss? So, okay, fine. So I'll come back to this. I is inversely proportional to omega. So when you bring your hands closer to your body, then the distribution of your mass, see, mass is distributed throughout your body. So when you bring your arms closer to your body, then the distribution of mass from the axis of rotation, that is R is going to decrease. If R is decreasing, I also will decrease. When I decreases, omega will increase. That is why when you're sitting on a rotating table and when you're rotating, when you bring your arms closer, you will rotate with the greatest speed. Or you can argue in this way also. The turntable is rotating. The turntable is rotating because of a torque. You're sitting on a rotating table. You're rotating not because a torque is applied on you. You are rotating because of the turntable being rotating. That way also you can argue. Is that clear, boys? You're sitting on a turntable which is rotating. That's the reason you're rotating. There is no torque acting on you. Are you clear? Someone was asking this question. Who was that?
I
Okay,
understand.
you take this way. No, you take this way. You are sitting on a rotating platform. The platform is undergoing a torque. You are rotating because the platform is rotating. There is a torque which is rotating the platform, but there is no torque, no force applied on you. Nothing is applied on you. You are rotating because of the platform being rotating, but the platform.
I just
Take
wanted to
it that
clarify,
way.
like
Okay.
how the
No, no problem. No problem. You can argue that way also. You can argue this way also. Nothing is being applied on you. No torque is applied on you. You're rotating because your platform is rotating. That way you can. Now I'll come back to this. Now look at this, boys. A man, I'm just drawing this. A man is sitting on a rotating table and he's stretching his hands with his arms stretched with 5 kilograms weight in each hand, right? Arms stretched, and look at this angular speed is 30 revolutions per minute. Then it is new 30 RPM. You have to convert it to RPS. Right? So 30 by 60 rotations per second. Then you have to go for angular speed. It is 2 pi nu. This is angular frequency, the number of times you rotate per second. Are you clear, boys? So whenever they give you the value RPM or RPS, that is the number of revolution made in 1 second. Then angular speed. Your angular speed, one second, do you understand the difference between that is more important, boys? See, when a body, suppose when a body undergoes a rotational motion, this, suppose if it starts from point, this body is just rotating about an axis. It starts from point A, comes back to point A. That is one complete revolution. The time taken for one complete revolution, we call it as frequency. A body is rotating about an axis. When it starts from point A, comes back to point A, it's one complete rotation or revolution. In that case, the time taken for one complete revolutions or rotation is your angular frequency. Okay. Now, what is angular speed? Angular speed is that, right, the body is at point A. After some time, the body reaches point B. It sweeps some angle. When the body is rotating about an axis, it sweeps out angle. It's a radius vector. Radius vector means what? The distance of the particle from the axis of rotation. Like you think of your R hand as well as the minute hands of your clock. As it is rotating, it sweeps out angles. So the angle swept in a given time, that is what is the angular speed. Omega is equal to theta by E. So this angular speed, you measure it in radians per second. Angular frequency is RPS, rotation per second. Where do you see all these things? Because RPM and RPS. RPM is an important factor you could have. Automobiles, do you see RPM? Automobiles, you see RPM, right? I think so. Where you come across in our automobiles, RPM and RPS. RPS will not be there. RPM is there. Just check, boys. Go for your automobile engineering. Just check what is RPM, because RPM.
Instead of RPS, there is rev per second, meaning like revolutions per second.
Revolutions per second. That's the standard one, because here they have given revolutions per minute. You have to convert it to revolutions per second. Now look at this, boys. A man stands on a rotating platform with his arms stretched horizontally, holding 5 kilogram weight in each hand, right? So the angular speed is nu is given as that, only that you need to be. So that is RPM. So I have to convert it to RPS. 30 divided by 60 rotations per second. Yeah. So omega will be equal to 2 pi nu. That will be in radians per second. Okay. The man then brings his arms close to his body with a distance of weight changing from 90 centimeter
It's
to
5 by 2,
20.
right?
No,
Angular
no,
speed.
which one?
The omega.
Omega is 2 pi nu. So this becomes half 1 by 2 RPS. So this becomes 2 pi into 1 by 2. So that this omega is pi radians per second, correct? Omega is pi radians per second. Because this is one of the important application-based question. Now look at total initial moment of inertia. See, moment of inertia, and one more thing they have given, the moment of inertia of the man together with the platform. The moment of inertia of the man with the platform. Even platform, you cannot rotate it faster. It shows some amount of resistance. So the moment of inertia of the man together with the platform may be taken to be a constant, and that is equal to 7.6 kilogram meter squared. So the total moment of inertia is the moment of inertia of the man and the platform plus the moment of inertia of the 5 kilogram weight. Now, do you understand this? The man is rotating on the platform. Sorry, the man is standing on a rotating platform. So the platform will also have a moment of inertia. The man is also having a moment of inertia. So the first part of the total initial moment of inertia is the moment of inertia of the man and the platform plus the moment of inertia of the 5 kilogram weights. So how far is your 5 kilogram weight, each of the weight located from the axis of rotation? See, you're rotating about an axis, right? The man is rotating about an axis passing through him. So your 5 kilogram weight is because when he's stretching his hands, how far he's stretching his hands? He's stretching his hands 90 centimeter away from the axis of rotation. So moment of inertia of the 5 kilogram weights will be m into r squared. What is m? M is the mass of the weights which he is carrying. That is 5 kilograms. So both his hands on both sides, we have to take the moment of inertia of both the weights. So that is the moment of inertia of 5 kilogram weights. So 2 into mass is 5 into how far are these weights from the axis of rotation? 90 centimeters. Boys, are you finding it very difficult? 11B, you want to have a, should I stop here or 11B?
Ma'am, we can do one more.
Okay. Boys, I'm just, do you understand what it is? The person is standing on a turntable. So this rotating table, the rotating table is having a moment of inertia. So that moment of inertia plus this is the man. So first and foremost, the moment of inertia of the rotating table plus the moment of inertia of the man. That is given as 7.6 kilogram per meter squared. Sorry, into meter squared. Next one, he's stretching his arms outward with 5 kilogram weights on each of his hands, right, which is 90 centimeter away from him. So the moment of inertia of 5 kilogram weights, that is mr square. So that's the reason. So this is 7.6 plus mr square. How many weights are there? 2 weights are there. So I1 becomes equal to 7.6 plus 2 into what is m? The weights 5 kilogram. How far they are located from the axis of rotation? 90 into 10 to the power of minus 2 squared. Right? Calculate these values, boys. Calculate. Let me see. Calculate this. What's the value? What will be its value? Just find it difficult then. So just write 15.7 kilogram meter squared. So when he's stretching his, so that is your moment of inertia, initial moment of inertia. So when he is stretching his hands with the weights 5 kilograms on each of his hands at 90 centimeter away from the axis of rotation, his moment of inertia is 15.7 kilogram meter square. Now look at the other part of the question. He is bringing his arms closer. So both the masses are coming closer. What is the distance? 20 centimeter. Now 90 is going to change to 20. So this is his initial momentum. Next, I have to go for final momentum. Now what will be the value? Have you copied this, boys? 5 more minutes. That's it. Have you copied this? 11B?
Ma'am, just
Yes, ma'am.
Now I will go for the next one. Now look at this. He's bringing the masses closer to each other. So what is
Could you go
I2?
back to the previous slide, please?
Okay. Shall I move back to the next slide?
Yes, ma'am.
Now wait, boys. Now it is this way, right? So now I2 will be moment of inertia of the man and the table plus the rotating table. So that is given as a constant value plus moment of inertia of 5 kilogram to 5 kilogram mass. Now this value I2 is a standard one. That is what is given as 7.6. Now this becomes of 2. So 2 into what is the formula? mr squared. Now here r is 20 centimeter because you're bringing your arms closer, right? So the weight becomes closer to you, which means it becomes closer to the axis of rotation. You're bringing your hands. In the previous case, the hands was stretched. Now you're bringing your hands closer to your body, which means your axis of rotation is passing through your body. So you have decreased the distance between the 5 kilogram mass and the axis of rotation. Boys, when you're rotating, how do you rotate on a rotating table? You're rotating about an axis vertically passing through the man. The man is rotating about an axis which is vertically passing through his body. So when he's bringing his arms closer to his body, so that distance of the 5 kilogram mass from his body is decreasing, axis of rotation. So that R is 20 into 10 to the power of minus 2 meter. So now you calculate, boys. This is 7.6 plus 2 into mass is 5 kilogram. 20 into 10 to the power of minus 2 the whole square. So now I2 comes to be
I2 be 8.
Okay.
Ma'am,
Now, what is- yes.
whether momentum is conserved or not, we don't need to calculate, right? Because
No.
we know that if torque is 0, the momentum is constant, right? Throughout.
Constant.
So whether it is
Okay,
like
fine. We'll complete this initial angular speed. Let us. What is the initial angular speed, boys? What was the question? 30 revolutions per minute, right? So now they're asking you, what is the new angular speed? Boys, what is the new angular speed? What was the initial angular speed? How many revolutions were given? 30 RPM. Now 30 RPM, I'm converting it to 30 by 60 RPS, that is half RPS. So what is the angular speed? This is initial angular speed, omega 1, 2 pi nu 1. So that is 2 pi into half. So is that omega 1 is equal to pi radians? Boys, is that correct? Is omega 1 is pi radians?
Radian per second.
Radians per second. So now they're asking you to find what will be the final angular velocity. When he brings the 5 kilogram mass closer to his body, naturally your speed will increase. So how will I find omega 2? I have to go for law of conservation of this numerical I'll finish it off. So by law of conservation of angular momentum, what is that? First, I omega is a constant. L is a constant. What is L? L, I into omega, that is a constant. Or I can write I1 omega 1 must be equal to I2 omega 2. So these are all the formulas which you have to use from the law of conservation of angular momentum. I omega is a constant, or I can say I is inversely proportional to omega, or I1 omega 1 must be equal to I2 omega 2. So you can calculate your omega 2 over here. So that is,
How do you get 1.57? Isn't it 15.7?
yeah, 15 point, sorry boys, it's 15.7, so 15.7 pi, omega 1 is pi.
We can leave it there, or do we?
No, you have to calculate boys, you need 3.14. What was the next part of the question? What was the next?
Is kinetic energy conserved? I think.
Okay, kinetic energy conserved. Okay, what will be the formula for kinetic energy? Half I omega squared. What's the kinetic energy is half I omega squared? Yes or no?
Yes, ma'am.
Okay, so now
Yes.
what is, okay, fine. What is, let us see kinetic energy of the first body, sorry, initial kinetic energy by final kinetic energy. So what should I write? Half I1 omega 1 squared by half I2 omega 2 squared. Half and half will get cancelled. Now, can you check this value? What is the value of K1 by K2?
I think we can leave it at pi only because the first one also has pi, so we can
Pi,
cancel.
okay, cancel it out. Okay. It was only a few minutes after this numerical. I'll stop. Now calculate this, boys. What will be K1 by K2?
Ma'am, angular speed means omega, ma'am.
Omega. Angular speed is omega, boys.
Okay, ma'am.
Okay, should I do this? What was I1? It is 15.7, correct? 15.7. This was 8. Omega 1 is 15.7 pi by 8.
Ma'am, we have to actually calculate this.
No need to calculate. You have to check whether K1 is, one second, whether K1 is greater than, it approximately comes to be 1.97, which means your final kinetic energy K2 is equal to 1.97 times K1.
No, ma'am, I think it is what it's conserved, ma'am. It's equal because
It's equal.
yes, ma'am. Because if you substitute 15.97 there only, right? The 8 and 8 will get cancelled,
But
and
our whole square, right? You have a
yeah,
whole square. Just check. It's a whole square term, boss. Just check. Because it's a whole square term. So you will have I1 and I2 15. One of the term will get cancelled, but the other term will still remain.
Okay, the other one.
It remains, which means your final kinetic energy is greater than your initial kinetic energy. Because you are gaining the angular speed. You're gaining the angular speed.
We are gaining angular speed because the this is reducing, right? The
Moment of inertia. Fine, boys. Thank you. I think so. I should not keep you more than this. Just write this, boys. Final kinetic energy. Thank you, boys. So you know, hardly we have done 3 numericals. So many. Okay, fine. Just you would have got an idea how to solve some numericals in this chapter. So you have your textbook. When you are free, just solve other numericals also, boys. Okay. So I'll stop.
Yes, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you.
Thank you.